I think if, say, I won $1 billion in the lottery, I would keep doing exactly what I'm doing now.
Meet Goldie, the co-creator of AlphaChip, the AI that revolutionized how computer chips are designed. Then came the opportunity of a lifetime.
We received an email from Jeff Dean saying, let's do a moonshot.
When she finally got her shot at Google Brain, reality hit hard.
When we showed that to like the TPU team, it wasn't even like they laughed us out of the room. They were like actually a little bit angry. Like, why are you showing us this thing? We don't care about this.
The pressure was crushing.
And every day that the chip is delayed costs the company enormous amounts of money. So even just the opportunity cost.
What is the magnitude of the money they were lost?
Like, it would be like millions of dollars per day.
The stakes couldn't be higher.
Make a mistake, maybe it costs $100 million.
$100 million, right?
The problem seemed impossible.
Our large pre-training data set had 20 examples in it.
Whoa.
That's insane from a machine learning perspective. So the state space is like, a simplified version is like 10 to the 9,000 like possible solutions. The vast majority of those solutions are invalid.
How do you solve the unsolvable with almost no data, million-dollar stakes, and the future of AI hanging in the balance? Meet Goldie, Senior Staff Research Scientist at Google DeepMind and co-lead of AlphaChip, the breakthrough project that applied reinforcement learning to chip design and was featured on the cover of Nature. With 11 years at Google Brain and a recent stint as a member of technical staff at Anthropic, Anna has been at the forefront of AI research spanning systems, language, and large-scale infrastructure. She holds a PhD in computer science from Stanford, dual bachelor's degrees in computer science and linguistics from MIT, and was honored on MIT's 35 Under 35 list. From developing dialogue systems as a student to building superhuman AI-generated chip layouts now running in Google data centers. Anna's journey reflects both scientific rigor and visionary ambition. Goldie's path shows how a spark of curiosity can grow into a career that reshapes an entire field. At MIT, a single lecture on spoken language systems inspired her to dive into AI and linguistics, building early dialogue systems before pursuing her PhD at Stanford. Her career at Google began with experiments like Project Amy and Smalltalk, exploring how AI could learn from language. But when deep learning started to outpace older rule-based systems, Anna made the leap, joining Google Brain during what she calls a golden age of bottom-up research. Backed by leaders like Jeff Dean, she collaborated with Azalia Mirhoseini, first tackling device placement for neural network, and later co-leading AlphaChip, Google's moonshot applying reinforcement learning to chip design. That collaboration bridged software and hardware, opening a new frontier in AI-driven systems. Let us get started.
Hi Anna, welcome to Founder Coho. You have amazing careers, co-lead of AlphaChip. I think it's one of the breakthroughs that really changed how the hardware is designed. And very honored to have you.
Well, I'm very honored to be here. Thanks so much for inviting me.
Absolutely, yeah. We'd love to hear about your early days. And can you introduce yourself to our audiences and listeners?
I would say that I don't know if there's like some strong boundary between myself as a person and a researcher, right? Mm-hmm. I think if, say, I won $1 billion in the lottery, I would keep doing exactly what I'm doing now.
So research is more a passion for you.
Yeah, passion for me.
Mm-hmm. Yeah, and I'm actually wondering that when did that passion start in your early days?
I guess like I remember when I was growing up, like in like kindergarten, you know, they would ask you like, what do you want to be when you grow up? And everyone else seemed to know the answer, like, oh, I want to be a firefighter or an astronaut. Mm-hmm. And I remember being kind of worried because I really wasn't sure. Mm-hmm. And then, you know, in high school, I liked everything. Like I liked, you know, French literature or math or like biology or, you know, I wasn't sure what I wanted to do with my life going forward. And then I did this summer program at MIT, which was like basically an introduction to discrete math, electrical engineering and computer science. And then they had these lunch lectures by various faculty. And one of them was about like spoken language systems. So this professor, Victor Zhu, described this idea of like a spoken language dialogue system, a computer system you could speak to and it could respond.
When was that?
That was like 2004.
Wow, that was like OG time.
Yeah, it was like crazy. But
yeah,
I was just like completely, like I could feel like my blood like pounding in my ears. I was like, this is what I want to do when I grow up, right? This is the most amazing, fascinating thing I can imagine. So yeah, so that journey, the MIT summer school, ignited your passions for the whole research area. Yeah. I know you later went to MIT. Was it because of that? Oh yeah, for sure. Like I was like, okay, I want to build systems like this. So I went to MIT. I studied computer science and linguistics. I actually joined that professor's lab.
Oh, that particular professor?
Yeah.
Wow.
Yeah, so I worked on dialogue systems. Yeah.
Wow. Yeah, tell us more about your life at MIT. How was MIT study life look like?
It was very intense, right? Like they say, drinking from a fire hose.
What was the dialogue system look like back in 2004, 2005?
Like completely different, right? You
Yeah.
have like a rule-based dialogue system. And it was like, in the case of the lab I was in, which is SLS, spoken language systems, like it was actually audio as well. And I remember like, I took the 6345, it's this like ASR, automatic speech recognition. We would actually read spectrograms as humans. Like you would look at the waveform and you could like say, oh, there's an R here or something.
Oh, yeah,
It was
I
like
remember.
using like signal processing and such, right? It was like completely different paradigm. Like,
How long does it take to learn how to run a spectrum? That sounds like a magic skill. Yeah.
I mean, like a semester, I guess, right?
A whole
but also
semester.
not just yourself to learn how, but also like to do signal processing to enable that recognition. Like, or I worked on like I made a domain specific like language that with a compiler in C or something. Like I don't know, it's just a completely different paradigm.
Yeah, I think back then, like there was, like you mentioned, a lot of rule based, so you kind of have to learn language very well in order to do research in the field. Is that true?
Yeah, exactly. Like I remember, like my goal was to build language models, right? And so I wasn't sure what the best way was. And I remember interviewing faculty, like 5 faculty who were on the sort of computational side of linguistics, 5 faculty who were on the sort of language NLP side of computer science to try to ask for their advice on whether I should do linguistics or computer science. And then I met my advisor that way and I, decided to just do both. But I think at this point, I don't think linguistics is super necessary for like the neural paradigm.
Yeah.
It was satisfying. But.
Yeah, I think is that in that stages was very, very important. And a lot of the learning people have on that has already been internalized as they develop this new paradigm of LLM.
The models find the rules. But back then it's like you would define these like elegant like parsing.
Yeah, like all
rules.
these structure, syntax trees.
Exactly.
Yeah. And I know you speak perfect Mandarin. Is that related to your major over there?
MIT doesn't allow triple majors, but so I actually did take enough like foreign language classes that I could have gotten a third major if that were allowed. But I think I would just take foreign language classes every semester that I was there, but for fun. Because for me, the reason I wanted to build like language models was because I thought maybe that would mean something like bring us towards understanding how humans can understand and generate human language. And so I like learning languages to try to observe my own process of acquiring a language. Maybe it gives some insight, right?
Yeah, exactly. How did you choose Mandarin? There's so many languages in the world.
I studied other languages too, right?
Oh, yeah. How many languages can you speak?
I speak English, hopefully, Mandarin, Japanese, French, some Korean, some German, some Italian.
Wow.
Some Spanish, I guess. But
that's amazing.
I think I'm just like very fascinated by the process of acquiring languages and like how you can do it optimally.
What is the first team did you join when you joined Google?
I remember it was funny. It was called the AI team, which is ridiculous. It was like AI at google.com was like the team's like alias or something. Yeah. It was Anna Patterson's team. She was my first manager.
What was the project? Was it related to the project you later work at Google Research?
So it's called Amy. It was basically this idea like maybe we should be able to benchmark AI progress by having the model like take like elementary school like reading comprehension exams.
Oh.
So we had the model would like read, or it wasn't even a model I would say, but it would the system would read a passage and then answer questions.
Yeah.
And we were hoping to make progress on that.
When was that?
That was like 2013.
Well, this was very early. I think it was before the most people like establish all these NLP benchmarks. I think.
Yeah, exactly. It was like a different era.
It was totally different area. Yeah. And how long did you work in that team?
It was like a year and a half.
And then later you started switch to the Google research team.
This was Google Research actually.
This was also Google. Okay, the first team was
So I remember I then worked on this team like doing like dialogue systems actually. It's called Small Talk.
Yeah, I remember that, yeah.
Oh, yeah. And I remember we were all on the same floor, so it really wasn't much of a change to that team. But I remember like I was working, it was again rule-based, and I was making this beautiful semantic parser. Like I think I joined the team and then like I tripled like the performance on the metrics that we had. But I could just tell that this was not going anywhere. Like I collected this large data set and then I tried like comparing the performance of this rule-based system that I had poured my soul into compared to like a very simple like neural baseline, and it was just there was no hope for
Exactly.
the human like rule-based
Exactly.
system.
Yeah.
Like that's when I decided I need to be working on deep learning, right?
Exactly. When was that?
2016.
2016. I think that was the time a lot of people realized a similar thing.
Yeah.
And I think that in the time before 2016, like everyone was talking feature engineering, adding the rules, even there was decision trees, and everyone was like, smart people would come up with all these tricks and rules. And I think 2015, 2016, that was a time, like, almost all fields, people started to realize that if you have an end-to-end learning system that can learn the rules, like gradually, like no human will be able to beat that.
Yeah, exactly. I knew I couldn't.
Yeah, exactly. Yeah. And then after you had that realization that you have to jump the ship to work on end-to-end learning system, like what project did you choose to do?
Again, I think that, like, I remember I had lunch with my friend Chris Ola, and he like encouraged me to apply to Google Brain. I'm not sure I would have otherwise even thought that they would consider me or something, right? I remember I met with Jeff, like I applied, like using,
you applied.
I applied to Google Brain. And
did you apply through the internal transfer portal? Or
I remember I think they had a abnormal process, I think. Like it was like way beyond the normal.
Exactly. I
protocol.
remember it was 10 to 1. Like only 10 to 1. Like 10 people applied to transfer Google Brain, only one get accepted.
I didn't know about that. Maybe I would have been too intimidated. But I remember like I think I was up for promotion, and I think Greg Corrado was like, maybe just use your promo packet as your application. And they had some kind of like committee of like Kwok and Jeff Dean and like Sammy or something.
Smart strategy. Yeah.
I was so happy when like I found out I got in. I just couldn't believe it. Like
it's
clearly like a life-changing moment, right?
Exactly. Yeah. And that was 2016.
2016. Yeah.
And so what was the first day that you joined the Google Brain team? What was the day look like?
I guess the interesting other part was that so I had this offer to join Google Brain, and then Jeff said that he could even sort of improve the situation. I could, if I wanted to, participate in this Google Brain residency program that hadn't previously existed.
Yes.
So he was like, we have this program, it's starting, I feel like June 20th or something. And you can take part in that if you want, even though you're full-time. And like I remember him showing me these like profiles of the people that like were, and it was like a crazy batch especially that first Google Brain cohort.
So you joined the residency program.
I joined the residency program, and it was like an amazing situation for me, right? Because I'm already full time, so I'm not like stressed out about conversion, but I also had this like complete freedom.
Yeah.
And I was like, Jeff was like basically like, you will have the freedom to like pursue your research interests, and if you want to like grow into a research scientist, because I was a software engineer at that time, right?
Yeah.
And it was like true, like
that's a fantastic program to be and
extremely lucky that you get to be part of that, right?
Yeah. So for many of our listeners who are less familiar about the Google Brain environment or the whole this research lab, and how would you describe the environment?
It's basically like the perfect research environment, like a golden age.
How does a typical day look like when you are working over there?
It was just like complete research freedom is like the backdrop, right?
Yeah.
So you can work on at that time, you could work on whatever you want with whoever you want. You could publish it, you could open source it. I think in terms of a typical day, just like a lot of coding, right? Like coding, like some, like at the time it was like before this like large scale like transformer paradigm. So like I'd even make like custom neural architectures, right? I'd be like writing some code in TensorFlow.
Right.
Like, running experiments, like writing papers, open sourcing code even.
Exactly. Yeah. I think it's a very awesome places. You basically like a playground for researchers. You can do anything you want, and you can be as crazy you want. Actually, craziness is encouraged in the whole environment.
Exactly. I remember there was like nose brain. There were like people that were like making neural nets to like understand smells or like discover exoplanets or maybe do chip design or whatever. Like I feel like it was very like bottom up, and like a lot of brilliant people too. So it was like really fun to work with pretty much anyone. on the team, right?
Yeah, it's like pretty self-organized, very flat organizations. And do you have a manager in the Google Brain? Do you?
Yeah, I mean, I still haven't had a manager, yeah.
But how does this manager and report relationship works in Google Brain? Is it traditional or is it more like a different role?
I think like less traditional. I think my first manager was Sammy Bengio. Like my current manager is Kwok Lee. It's just like, like this really brilliant researcher who has like very deep intuitions himself, but also like trusts. I think he's picky about who he hires and then he trusts them to do what makes sense. Like my manager would never like tell me what to do or something like that, right? Or even how to do the thing. It was like, what do I think makes sense to do? And then if I think it makes sense, then do it.
Technically, they still call the manager, but I think the role is very different than what people traditionally think manager is doing.
It's more like your lawyer within the performance review system, promo system or something maybe.
Yeah, it's more, but I think there is kind of a kind of formal structure they have to have it as corporate, but in reality, they all serve as your coach as you do your own research, and you're an independent researcher who are pursuing your own passion.
I completely agree with that.
Yeah.
But I think it's still like, such an honor to like say get to meet with someone like Kwok, right? Or
yeah, exactly. And I know that later you started work on the AlphaChip project, which is amazing. I think it's one of the most important breakthroughs in hardware design and AI plus hardware in the past few decades. In fact, I still remember I attended one of Jeff Dean's talk, and he was like, "It has always been hardware for AI. Now it's time for AI for hardware." It's very, very inspirational. Tell us more. How did you start the project? Like, what was the circumstance that made you decide to start the project?
We really want to like go to the origins of that. Azalia and we actually started out as like workout buddies.
Oh, workout buddy.
Yeah. So we would do like high interval training. So circuit training, I guess you could call it.
Okay, that's cool.
So we spent like a year as like workout buddies, and then we were like, oh, well, you know how you're like friends with someone, but you don't know if they'd be a good roommate, or it's always like nerve-wracking.
But you were in different
team
back before that.
We were both at Google Brain. We started on the same day actually.
Oh, same day! Wow.
But we didn't work together for like a year, and then we thought let's try collaborating. So we worked on this project we called it device placement, where it's like say you have a very large neural network, like maybe tens of thousands of operations, and maybe it doesn't even fit on a single GPU, or you could accelerate it if you were to do like parallelism, right? And so we were like, maybe this, we can treat this as an RL problem, have an RL agent, like assign each of the ops onto a different GPU or CPU core. We weren't even doing it on TPUs then, which is funny. And the reward signal can be just the runtime of executing that, like training or inference with that partition. So that was our first project together. We did it in like 3 weeks. Like we wrote like a bunch of code together.
Wow, 3 weeks.
Yeah.
Yeah. Was it type of like hackathon?
It wasn't, but it kind of felt like one in retrospect. We actually we had this idea, we coded it up together, we ran the experiments, and we wrote the paper in 3 weeks, which is insane actually in retrospect.
Yeah.
I think it was rejected the first time we submitted, and then we did a little bit of rewriting and it got into ICLR or whatever.
That's cool.
So then we were like, well, what can we do next, right? Like, what would be more interesting or impactful?
And one quick question, because at that time, you and Azalia are still in different team. So did you? We
were both at Google Brain.
Oh, but the bigger team. Now you're working on the same projects, and you two come up with this project idea.
I mean, like I said, like as a resident or just maybe as any researcher at Google Brain, we could just do anything we wanted, right? So
how this idea came to your mind? Yeah.
I think we just were thinking about like, what is a thing that we both find interesting, right? And what would be impactful. But I think when we were thinking, okay, like how do we take this to the next level though, right?
Yeah.
And like, what is another like much larger scale, much more challenging, much more impactful graph placement problem? And like, what is a problem that has this sort of recursive self-improvement like structure? And then we thought maybe chip design, chip placement, right? Like we thought maybe we have some edge here, right? Because we had worked on and gotten traction on a comparable or to us related problem.
Yeah. When was that?
Let's see. So it was like 2017, right?
2017,
End of
yeah,
2017.
Yeah.
And then I think Google Brain had this Moonshot program, which was starting for the first time. Any person could propose a moonshot, and you would commit to work for a year on something that, maybe it sounds impossible, but if you were to succeed, it would matter a lot, kind of thing, right?
Exactly.
It's a very competitive program.
I think that was time, we too met. Because I heard your pitch in the Moonshot project.
Oh, really?
And then
funny.
we grabbed lunch afterward.
Oh, that's crazy. I remember it was like we got 3 minutes to pitch, right? And then I think Kwok was like he saw our slide deck in advance. I think we had 21 slides, and then Azalia and I jointly pitched for 3 minutes. And he was like, oh my God, you're not gonna be able to get through all of those slides. But we did it.
Can you tell our listeners about what is this Moonshot project and why it was set up in the Google Brain?
So I think we thought, well, chips are the fuel for progress in machine learning, right?
Yeah.
As soon as you see those neural scaling laws, where as you scale up the number of the amount of compute applied, the number of parameters, the data, you just get better performance, right? So we're if we could use machine learning to make better chips to fuel the AI systems of the future, I think this could be really powerful, right?
Yeah, the chip design is a very important part, and also the area in which the RL can be very, very useful.
Exactly.
Yeah, take a step back. Who organized this pitch, and was it organized regularly, and how did you find the Moonshot pitch?
I feel bad. I don't remember exactly which person organized the Moonshot program the first time. Do you remember?
I don't know who initiated that. Yeah. But it becomes a regular thing.
I think, but when I pitched, it was the first time they had it. I remember Kwok had AutoML as a Moonshot, for example.
Yeah, I remember that one. Yeah.
I think it's really good because I think that it's a little bit of an antidote to this, one potential weakness of an organization that's doing bottoms up exploratory research is people could sort of individually do low impact projects or something. So to have this a little bit of force towards let's think about what would be really impactful and ambitious was probably good for the team, right?
Exactly. I don't know who organized this. I think we should find a name and give the person credit.
And the funny part was I don't think they actually provided additional compute resources or really.
No, they didn't?
or headcount or anything. But
okay.
I think just something about you are a moonshot, you have this banner that you can hold up. Even that's good, right?
Yeah. Because I never got a Moonshot project because my project was a recommendation system, so it's why it's called Moonshot. And but I didn't know they didn't provide additional computer resources.
I think if you wanted to say request leads resources, maybe you could have a quicker line to leadership, but I don't think that was true actually.
But back then, I think the resource was never a problem.
Yeah.
There's plenty of free GPU back then, and then the each of the model training doesn't take that many GPU back then.
Exactly.
Yeah. That's cool. Yeah. So let's dive back into the AlphaChip projects. So you mentioned about then you started to think about the bigger problem, and chip design is one of them.
Yeah.
And then how did you turn this idea to something that actually is more concrete? And did you choose some design partners or to work on the chip design?
Yeah. I remember Azalia and I, we spent a lot of time interviewing chip designers across various parts of the stack, right? Because there's multiple stages. And we wanted to understand where are people spending time, what's hard, and also which problems had a shape that we thought we could help with, or that maybe an RL or neural approach could be helpful for. And that's kind of how we would narrow in on our goal was to do end-to-end chip design, but where would we start, right? We thought chip placement optimization. And we partnered with the TPU team. Oh,
you partnered with TPU back then? Yeah.
Because we thought, okay, what's more exciting than helping build AI chips, right?
Yes.
Because TPUs are the AI accelerators at Google.
Yeah. So what problem TPU team was facing made them to be interested to collaborate with you?
I mean, there are an entire team of say, for example, this is just one of their many problems, but physical design. So how to generate a manufacturable chip layout that's high performance and has no defects. They have teams of people spending weeks, months. They have PhDs in this area. And every day that the chip is delayed costs the company enormous amounts of money. So even just the opportunity cost.
What is the magnitude of the money they were lost?
It could be millions of dollars
Millions
per day.
of dollars, yeah.
Just in opportunity cost.
Yeah, it's a very high stake situation.
But if you make a mistake, maybe it costs $100 million.
$100 million, right?
Yeah.
So if you make the wrong design and then they started to manufacture and then hundreds of millions of dollars gonna waste
you make a wrong mask or something, like you're just...
Exactly, yeah.
It's catastrophic.
Exactly. And I wonder that because the problem we are solving, there's many people apply RL to different problems. So for example, I was applying RL to recommendation system. If you make a mistake, totally fine, just say like a bad YouTube video.
Or maybe like you radicalize someone or something.
Yeah, but that could happen. I think that the guardrail is still needed for those cases. And for your cases, I think stake is particularly high. And what was your approach to minimize the risk?
I mean, I think one thing that's like better about like the chip placement setting would be you can do it offline, right? So you can do extensive like simulation of the design that you generate.
So you implement like simulators and experiment.
There are commercial tools. They cost like say $1 million per license per year, and they can take like, up to 72 hours to run, but they will calculate, high fidelity metrics. So it's something that you can almost treat as ground truth. Like obviously you can't like build the chip and then test it because that would be way too expensive of a way to check the quality of your solution. But you can get, some signal before you build it, which helps a lot, right?
Yeah, that's a great point. Like one thing I realized back then, I think 2017, 2018, all the RL researchers was like, basically you have a hammer, you are trying to find a solution from that. And one of the indicator I realized that whether an RL can be successful in the field is whether there is an existing simulator from that. Is that feel the same way or different? Yeah.
I guess so one interesting thing I would say is I feel like there's a divergence between industry and academic research in this area. So when Azalia and I first started working on this, we looked into papers and we're like, oh, people optimize half perimeter wire length or something like that, right? And so we code up some RL agent that demonstrates that we can minimize half perimeter wire lengths, which kind of seems like it's a nice proxy cost, right? You can calculate it quickly.
Yeah.
But when we show that to the TPU team, it wasn't even they laugh us out of the room. They were actually a little bit angry. Why are you showing us this thing? We don't care about this. Metric doesn't mean anything to us, right? So even finding out what is the thing that they actually use to make decisions, what are their real metrics, was actually somewhat challenging.
Yeah. You mentioned a great point, which is the gap between research and production. I think we still hasn't, fast forward now, almost 80 years later, we haven't really still sorted that out. There's still a gap between the research, the metrics you use in research, or the benchmarks you do, and what actually the production team is using. Exactly. Yeah. And do you think that in the past 80 years, we have been making progress on that?
I mean, it depends which domain we're talking about. I think in chip design, I think there was, or physical design, I think increasing divergence.
Oh, so increasing divergence.
I feel the academic community was solving this beautiful applied math problem. They have analytic solvers, they optimize half perimeter wire length, maybe some kind of approximate metric of routing congestion, but often not. Whereas in the real world, when you're trying to actually build chips at sub 10 or sub 7 or even sub 5 nanometer technology node sizes, they're looking at completely different metrics, right? So they're looking at routed wire length, horizontal vertical congestion, various timing violations, power consumption, area, related to yield. So it's
it's a lot more
very
details,
divergent.
Very divergent. And do you think this trend will continue?
I mean, I think with our paper, we really tried to push things back towards something more what the real problem is in industry. We reported metrics from this commercial EDA tool on modern chips with sub, I guess I can't say what nanometer process, but
right,
yeah. And I think we saw some other papers then for reporting metrics that were the actual ones that physical designers use to decide which layout to send for manufacturing. So hopefully we some influence.
Yeah. I think that's also the challenge of industrial research team, because when we do the research in Compline, we usually will pay more attention to what actually works. And then, but when we publish these results in the research community, they don't necessarily care about that. And they often care more about what is the theoretical value providing, or whether how they can reproduce it. But in real world, a lot of things, it takes an enormous amount of computation to reproduce.
I mean, that was the other weird part is like, I think some academics felt like, oh, like, you know, say AlphaChip used a lot of compute. Like, it's just like we use like 16 GPUs for like 6 hours to like, that's not actually that much compute. You're like, you know, people are spending like, I can't even say how many GPUs for how many months for training like large language models. Like the ratio is just absolutely ridiculous, right? Like, you're like not using that much compute.
I think you mentioned another great point, which is not just the divergence of the evaluations between academics and also industry research, but also the capability or the focus. Because like for 16 GPUs, for most of the research lab, they don't have. So they couldn't reproduce. But for industrial standard or any like labs like the Gemini or Anthropic, 16 GPU is nothing at all for that. So these gaps of the computational resources that is available to the industrial research lab and the academics is also widening.
I guess like I don't know if like I'm so convinced. I mean, obviously if you're actually building a chip, then there's just no question that it's worth that compute, right? Like the stakes are incredibly high. Like it's like TPU, like IP for TPU is worth like, I mean, I shouldn't even say it, but like, but I think on the academic side, like, you know, say some lab that was like interested in our work, like they had like won like a multi-million-dollar grant from NSF to do AI for chip design. Like I'm pretty sure that they could afford to, you know, run 16 GPUs or 20 GPUs for 40 hours and pre-train or something. That doesn't really make sense. Like the cost is really not that much, right?
I think it's also the emphasis, because traditionally they would be putting more emphasis on the theoretical innovations rather than the practical innovations, like in the school evaluation system.
Sure,
I also want to dive into another topic related to the AlphaChip, because I know this is a project that also Jeff Dean, he's super passionate about it, and you and Azalia and also Jeff Dean work very closely in this project. And he's a legendary person in the whole industry as well. How did you meet him?
I mean, I met him actually. He was trying to convince me to join Google Brain, which is not too hard for him, right?
What was the first meeting you had with him? What was your first impression on him?
Actually, my first meeting was I was like walking with this, you know, Ke. Our teammate at Google Brain. We were talking in Chinese for some reason. And then I think Jeff Dean was like walking behind us, and I guess he overheard us speaking in Chinese. And he was like, oh, my daughter wants to learn Chinese. Can you give her tips or something? So actually, that's how I met him originally. But
that's funny. I know we both also speak Chinese a lot.
Jeff never asked you for your tips, I guess.
Maybe I should speak more with you. Cool. And then later you reconnect, like you work more closely when you started AlphaChip project?
I think Azalia and we worked on this device placement work, and Jeff was a co-author. I remember like we had discussed the idea with him, but then we were so bad. Like we gave him a draft of our paper, I think like the morning that it was due or something into the conference. And then he was like, oh, well, maybe you could run these additional experiments. And I was like, maybe Jeff Dean could run these experiments in like the 3 hours left, but I'm not capable of that. And so, we had collaborated on that paper previously. And then I remember Azalia and we saw this like announcement for the Moonshot, and we were like, maybe we could do like ML for chip design, and systems optimization. Maybe that would be impactful. But we kind of wanted to propose that, and we wanted to see if Jeff were interested, right? And so we were writing this email together, like saying like, okay, we don't want it to sound too crazy, but you know, maybe he would find this interesting. And so as we were writing this email, we received an email from Jeff Dean saying, let's do a moonshot on
what a coincidence. You were thinking the same thing.
Yeah, exactly.
Before you write, and he messaged you first.
I was like, okay, well, if Jeff thought it was a good idea, then maybe we're not that crazy, right?
That's cool. And in fact, that I think one of the like one of the reasons why everyone loves Jeff is he's so humble. He's actually helping so many projects in Google to move forward and encouraging people. Exactly like you mentioned, like a lot of us when we think about we always don't have enough confidence. Like we think it's crazy or not. But when Jeff says he's do it, then then why not?
I think he's like a deeply like technical person, right?
Yeah,
but he's also optimistic, which is nice.
Yeah.
Right? He's very fast too, right?
Yeah, he's very, very fast.
Like he can immediately understand sort of any idea or result you might share with him. It's kind of exhilarating, right?
Yeah. It's you immediately get a positive feedback after like people understand you, especially a person with such a steady leadership and such a track record, understand you right away. I wonder in the projects, how does the work with Jeff look like? Do you do like regular meeting? He give you ideas? Like how exactly collaboration work?
I mean, I think we like shared our proposal with him and got feedback. I think the first year of the project, he actually would come to our weekly meeting with the TPU team, which was pretty cool. I remember being kind of nervous, like I better have some like good results every week to show this RL agent better learn something really. I think like that, I guess that was how we would, and then we had a monthly lunch with him. So we would discuss like ideas and results or like, oh, this, like we're having this like difficulty, like we're thinking about solving it this way. What do you think?
Yeah, exactly. Yeah. And I know that like, especially in, for any project related to RL in early days, it hasn't been smooth. Like back then, 2016, 2019, that everyone who working on RL was a very tough moment back then. And you're working on the AlphaChip, the device replacement. I'm very curious about your experience over there. Was it smooth? Did you get it working in the first try, or did you face a lot of obstacle in the process?
I think the device placement project, that was pretty fast, right? Like to get to a good result. Yeah. Maybe that's just, I think in that case, it's because the reward signal was so clean, right? Because you can just you create a partition and then you can just do a forward pass, a backwards pass, parameter update. Maybe you do it 10 times and take the average to reduce variance. But you have a very fast and very aligned with your true objective reward function, right? So it's an easier setup. In this case, it's very complex, the true reward, very hard to evaluate.
You mean the chip design?
Yeah,
it's much harder.
Because if you look at what the chip designers care about, it's 8 different things, right? And they are complex to evaluate.
Oh, so can you tell us what are the chip design? What are the 8 components in this?
So I guess one of them would be routed wire length. So what is the length of the wires needed to connect all the components that you've placed onto the chip? And there's these memory components SRAMs, which are maybe in the order of hundreds of those, and then there's millions of these logic gates standard cells, and it's all connected by wires. So it's this graph you're placing onto this highly granular canvas. So the state space is a simplified version is 10 to the 9,000 possible solutions.
10 to the 9,000.
Yeah, this is if you make various simplifying assumptions, and the vast majority of those solutions are invalid. So it's
yeah, that number feels bigger than the molecules in the universe.
I think that might be true.
Yeah.
This is kind of scary, right? It's this daunting problem. And then in terms of the cost functions, you're okay, what is the length of the wires needed to connect them? There's another metric, which is absolutely, it's a blocker, routing congestion. So is it even possible to, given the routing resources available on this chip, and I've been kind of presenting as if it's you're placing onto a 2D canvas, but that's not true. It's 3-dimensional, right? Because you have some number of wafers. And so you're placing components, and then you need to have wires route in various, at each XY coordinate along in this chip, you can only route one wire, let's say.
Yeah.
And so if you place it a certain way, it may be just actually impossible to connect these components. And then there's timing. So the signal.
A lot of constraints as well.
There's a lot of constraints.
Yeah. And then this sounds like extremely complex problem to solve. And how did you do this with 16 GPU? That feels like nothing to solve this problem. Yeah.
The real issue is that we had so little data, right?
Yeah.
So because we have so little data, it's there's some limit to how much GPU we can even leverage, right?
Yeah.
So we're talking like our large pre-training data set had 20 examples in it.
Whoa.
That's insane from a machine learning perspective. I think RL was like key to kind of making this tractable, because in some sense you could think of RL as generating labeled examples. Like you have some chip you're trying to place, and you can try many, many times to do that, and you can label the outcomes with your reward function. So you're in some sense expanding out your data, but like 20 examples is so few, right?
And how did you make this RL to be able to learn with such a few amount of data?
I think the key was like representation learning, right? So this is in the sort of
for the audience with like less background like of the ML, what is a representation learning?
So it's like, how do I basically allow the neural network to see, or the RL agent to actually see or understand the inputs in a meaningful way, right? So like in, language models, they like ingest words and then they create some, embeddings of their meaning, right? Yeah. In this case, like we want to ingest like a chip that we want to place, which is, millions of standard cells and maybe up to a few hundred macros connected by wires, and maybe some state of the canvas. Like we formulated it as like a sequential placement task where we place each of the components. Yeah. But how can you represent like the progress so far? Like some parts of the chip you've already placed things onto and you can't put things on top of those. So how can I make the neural network or agent see like what's going on? And then learn from it, right?
Yeah. So is my understanding correct that it's basically a very advanced model to be able to understand what's going on in the current placement?
Exactly. Or in like the state of the thing that you're placing as well.
Yeah.
What is the relationships between different components on the chip? Like which ones need to be near each other maybe, or something like that, right? And
then that representation learning is the one that you use the 16 GPU to train?
So we have basically an encoder that takes, creates embeddings for this, like some kind of neural representation for the input. And then we pass that into a deconvolutional neural network, our policy network, to generate a probability distribution over like, where should we place the next component onto this 2D canvas?
Right? Exactly.
And then a value network too.
Exactly, yeah. And I think you also touched such an interesting point. I want to dive a little bit deeper into that. You mentioned about encoder, and you also mentioned about earlier the representation learning, which everything here is basically trying to understand the input and turn that into certain representation, which can be the embedding. Yeah. And encoder back then was extremely popular at Google. I think it eventually need also the BERT, that the representations of a language, which then become the first really commercial, like popular transformer models, and then everyone started to. So this like all this project we did accidentally kick off all this another thread of large language models. I wonder what is your thought about like the paradigm that is evolving in this vibrant research community? Like you mentioned, like you're working on a chip design, you were using RL. I was working on RL with reinforcement learning. Some other team were working on these encoder things. Yeah. How did you got ideas of like using this representation learning or encoders? Was it related to the environment that you were in, just like some lunch conversations or read some papers?
I think it was more that, like we thought, okay, we want to train an agent that's like capable of doing this general task of generating high quality layouts.
Right.
But what we found was, at least initially, we had so little data, but even that little data that we had, we weren't getting anything out of it. So we would like say, we're like, let's have this agent place a bunch of tips and like learn from that. It wasn't learning anything actually. So, it was like, you might as well start from a randomly initialized, like if you had some new chip that you wanted to place, you were just as well off to start from a randomly initialized policy as the one that had experience on these other chips. And we thought that didn't seem like, there's something good if you spend 24 hours and you get like a superhuman layout, that's worth something, but it felt like there was something fundamentally less interesting about that setup, right? We wanted to actually be able to like learn from experience. And so that like, we were looking into like, why is it that we're not able to leverage pre-training or RL pre-training? And when we looked into it, it seemed like the value network was just giving insane predictions of the quality of the chip. Like it wasn't generalizing across different inputs. And so we thought maybe there's something wrong with the way we're feeding information into this network. Like it's not actually taking in a meaningful representation of the chip that generalizes across different inputs. And so we put a lot of effort into exploring different representations that would be really well suited, like had the right inductive bias for our problem. And we ended up with this like novel edge-based graph neural network that could generalize, like we could say from this embedding predict what the reward signal would be. And then once we had that, we could use it as the encoder. And then we generalized across chips.
Yeah, exactly. I think that one theme that how you're talking about, and also many team back then was like how to make the model more generalizable.
Yeah, exactly.
Yeah.
I remember one of our Nature reviewers was like, because we were like very excited in our Nature paper about how we saw this generalization. And he was like, isn't the bigger breakthrough that instead of spending weeks or months like of human effort that in say 24 hours, you could from scratch generate a high quality layout that was superhuman? Like, why do you care that you can do it in like 6 hours after pre-training? And I was like, maybe it's just as like a deep learning nerd, that seemed like, I think it matters actually, because then you can move towards like 0-shot placements or something like in like a second at just inference time generate a layout if you did enough pre-training. I think it does matter.
Thanks for watching the full interview. If you got value from this conversation, please like, drop a comment, and subscribe to Founder Coho. We've got more founder insights and deep dive interviews coming your way, so don't miss them. See you in the next one.